Hello, my name is Meabh MacMohan, and I will be talking today about DILIc, which is our AI-based classifier to classify literature as either related to drug-induced liver injury, or DILI, or unrelated to DILI. This is a short talk to complement our poster. If you would like to hear in more detail about this project, why wouldn't you? My colleague Sanjay Rathé is giving a talk at this conference on the 29th of July at 11:40 a.m. And it's a full-length talk. He'll be going into much more detail than I will have time to today. So this project was in response to the CAMDA challenge. DILI is a class of adverse drug reaction which causes problems in the clinic for patients, but also in research settings. It's a frequent cause of acute liver failure and also a major cause of attrition of novel drug candidates. Currently, the main route of obtaining DILI-related data from studies is manually trawling the literature for DILI papers, which is an inefficient process. It's prone to human error. So the challenge by CAMDA was to develop a classifier capable of identifying papers as either related to DILI or unrelated. In response to this, we developed DILIc, which is an AI model which combines natural language processing and machine learning methods to perform this classification. We combined the title and abstract information provided to us by CAMDA with data related to drug side effects from publicly available databases which contain information related to adverse effects, which added extra confidence to our classification. So CAMDA provided us with a curated data set of 50% DILI positive and 50% DILI negative papers. So we got the title and abstract, and the discovery set we were given was about 14,000 papers, and they held back 14,000 papers to test the models. So we split our discovery set 80-20 into training and testing sets, maintaining the 50-50 DILI positive, DILI negative split. And then the first step that we did was natural language processing. We used sentence segmentation and word tokenization to transform the title and abstract text information into a tokenized list of words more interpretable by a computer. We used lemmatization to retain only base words as keywords. For instance, maybe adverse effects. Adverse is fine, it's a base word, but effects, affected, effective, so the base word is effect, so we've retained the base word. Then we filtered out words that we considered not to be very useful, including stop words, such as at, the, be. So we retained only keywords that were nouns and adjectives. But we did not just consider single words would be useful, but also longer strings, so pairs or triplets. For example, induced hepatotoxicity is more meaningful than induced. So the pair of words would have a higher weight than a singleton. And after this natural language processing, we did pattern mining. We used an a priori machine learning algorithm to establish the frequency of the keyword or keyword set and its subset in terms of the number of papers in which it appeared, DILI positive or DILI negative. At this stage, we included the information from the external data sets. So we used the FDA approved drugs list and the CIDR adverse effects data set, both of which contain information related to adverse drug effects. For both data sets, we extracted a list of drugs with DILI listed as an adverse effect or a warning, and updated the weights of the keywords weighing the presence of these drugs as higher to be associated with DILI. So in the end, the weight of a keyword was calculated by its frequency with relation to DILI positive or DILI negative, the length of the keyword set, and inclusion or absence from the FDA or CIDR adverse effects list. and the final model was trained, the final vector of keywords was trained on various well-known machine learning models. The most effective of which was a gradient boosting machine, which on our held-out test set had 94.76% accuracy, and on the held-out set 50% DILI positive, 50 DILI negative. It maintained a high accuracy on the unseen 50-50 positive negative set provided to us by CAMDA, which is about 14,000 unseen papers. It had an accuracy of over 94%, but CAMDA had an additional data set for us to test on, and this external set of only 2,000 papers was not neatly split 50% DILI, 50% not DILI, which would be more reflective of real-world data. And we were pleased that on the additional external set, we had an accuracy of 90.25%, and the recall value of over 97%. We also trained our model using just the abstracts and then sequentially including FDA insider data sets, so we could actually see that the inclusion of these data sets was improving the model. To make this available to other researchers, we developed an R Shiny app, which will be released soon to deliver this tool in a more user-friendly way. It is already available at the link on the poster, and it's not just related to DILI. So a user can select any adverse effect and upload a list of papers to get the label whether it's related or unrelated. Although the results of this DILIC are quite satisfactory, we plan to continue tweaking the weights going forward. Thank you.